So today we are doing Lab 4 on oscillations. This experiment involves analyzing the motion of an object attached to a spring. It will experience the spring and gravity force as it oscillates. We will input the raw data and model it to see how well it can be modeled. In addition, we will derive all the energies related to the system and see if the energy principle withholds in this experiment. The energy principle states, if no energy enters or leaves the system, that energy should stay constant. The results of the experiment show that the observed motion very closely follows the motion that is described in the model. Also, the energy principle seems to stay true in this example, and all energy is retained. Now let's move on to how we calculated the data for this experiment. We calculated the energies of the system by knowing that no work was added or done to the system. So to conclude from this, total energy should equal 0, and this energy is comprised of the kinetic energy and the potential energies of the gravity and the spring. We know that the kinetic energy is 1/2 mv squared, and that the spring potential energy is 1/2 spring constant times position squared, and that gravity potential is mgh. We also use the spring tension formula to derive spring stiffness and relaxed length, because we know that the total spring force will be equivalent to mass times gravity. In our code, we use Newton's second law to update the position of the object as it moves. So we're going to take the video and model it in Tracker. After we do this, we will use the observed motion to compare to our model. So to find out how to find the spring stiffness, we will use the time in between the intervals of oscillation to calculate t in our spring period of oscillation. Using this t will get us our spring force constant that we will use in our model. This motion will be exported into a CSV file, and we will use that to later compare to the model, construction, and observed motion. Here's some important lines of code. First, we see how we imported the spring constant. We found out the relaxed length of the spring using our spring force equation, where mg equals spring constant times the length minus the relaxed length. Then we'll also set up the kinetic and potential energies that we will use to make sure that it fulfills the energy principle. We specify the kinetic and potential energies by simply using their formulas and inputting them into the Python code. While watching the model and predicted motion in action, we see that the model closely follows the observed motion but is not perfect. However, we conclude that it is a good fit and we can represent the model mathematically using what we have. The red ball represents the observed motion we got from Tracker, and the blue ball represents the one that we're using in the model. In this picture right here, they are in contact, so it shows that it's pretty close. So for the what if questions we have, is the energy principle satisfied? So we look at the graph that we got by modeling our data. Here we have kinetic and potential energies modeled here. In the middle, there's the yellow line that represents the total energy. Since the yellow line is a total of all the energies, and it stays near 0, we can say that the energy principle is satisfied because there is no energy entering or leaving the system. How fantastic. We see that the green and blue lines added together seem to be the negative of the red lines. If we add those two together, we will get 0, and that's how the energy principle works here. When we modeled our data in Tracker, we got time, x position, and y position. When we look at the graph of the x position and y position separately, we notice that it seems like there are two different periods of oscillation for these two movements. So here we can see that the first graph here is observed in the x direction, and the second is observed motion in the y direction. The y direction seems to have a faster period. In fact, after doing the calculations that we did earlier, but using the x direction instead, we see that the x direction makes a full rotation in 1.68 seconds, while the y direction makes a full rotation in just 1.52 seconds. This simply means that the two periods are not the same, and that the original change in motion was slightly bigger in the y than the x direction. To conclude, oscillations can be correctly modeled, tracked, and observed, just as in real life, and it works out pretty good. Also, the energy principle stays true in this example,